Hi, it's Mr. T here. Hey, this video is going to go over the topic or the standard of chemical reactivity, that is Achievement Standard 91166. Understand chemical reactivity in 90 minutes. So we're going to see if we can cover the whole topic in preparation for your upcoming exam. So the first thing we're going to look at is reaction rates. So how do we measure the rate of a chemical reaction? So when two reactants react together, then we can see that they are reacting the following ways. We can see a color change. We possibly could see gas being produced. If we place the reaction on a balance, we might see a weight change, or we might, with a pH indicator, notice that the pH is changing. So we can measure any of those four things to work out the relative rate at which a reaction changes. Of course, when we're talking about gas production, you could see that reaction is happening quickly if lots of gas has been evolved, and you can collect that gas and you can measure it in an inverted measuring cylinder. Okay, let's move on. So, collision theory. So the basis of all explaining the effects of reaction rates is the idea of collision theory. Now, collision theory is the statement that in order for a reaction to happen, then the two separate reactant particles must actually hit each other and collide before they can react. Okay, so I mean, it's kind of common sense, but we have to make sure that we understand that in the first place. So if they're not actually going to hit, they're not going to react, or if they're going to hit more frequently, they're going to react more frequently. So they must react. The second thing that they must also do is when they hit each other, they must have enough energy in that collision to form a chemical bond. Okay, so there has to be enough energy in order for the chemical bond to form. And the last thing that's mostly not as important that we have to write in the explanation is that sometimes they have to be orientated in the correct direction, or most times they will be, but that's kind of covered in when we talk about that they need to hit each other. We assume they need to hit each other in an optimal position. So the reaction rate is a measure of the number of particles that have had a successful collision in a given time. Successful reaction, I might say. To increase the reaction rate of a reaction, we need to increase the chance of the particles having a successful collision. Okay, so we're going to make it more likely that the collision is successful. And remember, to have a successful collision, two things have to happen. You have to hit, you have to have enough energy when you collide. We can increase this chance by exactly what I've just said here, increasing the frequency that the particles hit each other. And we can increase the average kinetic energy of the particles. Now, I think about it in the following way. I've got a classroom that I teach my chemistry in, and there are 20 students in there. Now, if I just ask the 20 students to put blindfolds on and walk around the classroom, they're going to have collisions every now and then. Now, what's going to happen is some of those collisions will result in the student getting a bleeding nose, right? Because they've hit each other's head or something. That's not the best thing, but it might happen. So if I'm taking that as a successful collision, right, or as an indication of the number of collisions that there are, in order for them to get a bleeding nose, they have to hit each other. Now, if I wanted, I don't really, but if I did want to increase the number of students who had bleeding noses from these collisions, the two things that I could do to do that is to increase the frequency of the collisions, make it more likely that the students would collide, and I could increase the energy that they collide, so make them collide at a more energetic rate. They'll be moving faster. Okay, so if I made them move faster, they would have more frequent collisions. They would also, when their collisions would have more kinetic energy. Both factors would influence whether they would have that negative outcome. So when we think about the factors that influence collision theories, there are four clear ones. There is the concentration of the reactants, so that's how many particles there are in a given unit volume. There is the temperature, so when we increase the temperature of a substance, we are increasing the kinetic energy of the particles, so they move faster. Surface area, so when we break a larger piece into smaller pieces, we have more surface area, more of the reactant particles are exposed and are able to collide with their other reacting particles. Reaction. Catalysts, okay, these are a special chemical that may be added to a reaction that facilitate or make it easier for the reaction to happen. Okay, let's look at concentration first. So here's an example of a solution that has two reactants in it and they are at a specific concentration. I'm going to call this a low concentration. So reaction A, which are the red particles, and reaction B, that are the blue particles. In order for this reaction to occur, those two have to hit each other. Notice in my diagram that I'm showing the velocity or the speed of, well, it's actually the velocity, but the speed of the particles using the arrows. The arrows are showing both the speed and the direction, with a larger arrow meaning they're going a larger speed. Now, interesting to know, when you have particles in a solution, they're going a random amount of speed. But if I wanted to talk about concentration, what would happen if I increased or made more particle A per unit volume? So here I've increased the concentration. Now if you look at these carefully and you think about how the particles might move based on the direction they are going to move and their velocity and their speed, you might see that in the second high concentration example, beaker, the particles are, because there are more particles per unit volume, there's a bigger concentration, higher concentration there. There are going to be more frequent collisions of the red particles and the blue particles. Now, because there will be more frequent collisions, we will also increase the amount of collisions that have enough energy to overcome the activation energy. So there will be a higher frequency of collisions, and there will be more effective collisions because more of those collisions will have the energy required just because more of them occurred. And that's how concentration affects or improves the reaction rate. What about temperature? Well, temperature is an interesting one because there are actually two independent factors. So if we increase the temperature of a solution, so we're increasing the temperature of a solution, say from 20 to 50, what's actually happening on the particle level is the kinetic energy of the particles has increased. Now, if you remember if you've ever done physics, you know the equation that kinetic energy equals half the mass times the velocity squared. Then velocity is proportional, it's actually to energy. So what I mean by that is if we increase the energy, we also increase the velocity. Okay, so because I increase the kinetic energy, the particles are moving faster. Because they're moving faster, they will have more frequent collisions. We think back to that analogy I made about students running around in the classroom, possibly getting a bleeding nose, right? Now, we are going to get more of those events happening if the students are running faster, because there will be more frequent collisions, and therefore because of that, it's more likely some of those will result in an injury. Also, because we have more kinetic energy, this is the separate independent point, that the particles are likely to have enough energy to overcome, are more likely to have enough energy to overcome the activation energy, and more of the collisions will be successful. So we actually need to stress two independent points here. One is that, so the thing that's the same with both is kinetic energy is increased because the temperature increased. But because the kinetic energy increased, the speed of the particles increased, they have a higher frequency of colliding. Also, because the kinetic energy increased, there is more energy going into the collision on average, so more of the collisions will be successful. Overall, there will be more successful collisions. That's temperature. Surface area. Okay, we can see a picture here of our red substance reacting with our blue particles. Now, the reaction can only occur when the blue particles hit the red substance on its surface. And this is a small surface area, but what I could do is I could take the substance, right? Here it is here, and I could cut it into smaller pieces. Now you might see when I've sliced it down both vertically and horizontally, what I've done is I've exposed new areas of this piece to the particles when they're in the solution. Now because of that, that means that we're going to have more frequent collisions of the reactant particles with the substance that we have. Now we have the exact same mass or the same amount, the number of moles of substance, we just have more surface area. Now the particles will have a higher frequency of collisions. Now it's important when we talk about both this and temperature and concentration that we use the phrase higher frequency. You could replace that with there are more collisions per second, but you can't just say there is a higher likelihood of collisions. You have to put some type of reference to time. So you have to say more collisions per second or higher frequency, which is just by definition means more things are happening per time. So because you have more frequent collisions, because you've got more exposed area, more of them will have enough energy to overcome the activation energy in a given time, and there will be more successful collisions per second. Don't be afraid of just putting that phrase in at the end, that there will be more successful collisions at the sentence per second. That's a good concluding statement. You also might at the end say, and therefore this will have a faster reaction rate, depending on the context of the question. Okay, catalyst. So a catalyst is, well, a reaction without a catalyst, we would take A and B. They need to collide with enough energy, remember, so for a reaction to happen, they need to have a collision and they need to collide with enough energy to overcome the activation energy, and that produces the product. That's fine, but only the particles that have enough energy are going to have a successful collision. If we use a catalyst, so this yellow object here is an example of a catalyst. What can happen? The two particles here actually have a lot smaller energy, and really they just need to go in and touch the catalyst there, and the catalyst will hold them adjacent to each other until they form a bond, and then the catalyst will leave. I mean, that's a rather simplistic diagram of how a catalyst works, but essentially a catalyst improves the chance that the particles are going to have a successful collision. Once they've had a successful collision, it moves away, and then it can now be used to help other particles collide. Now, with a catalyst, what we say is the catalyst provides an alternative pathway. So the particles don't just have to hit each other with lots of energy. The particles can also just hit the catalyst with a small amount of the energy, and the catalyst will join them together, right? So it's an alternative pathway. Now, so remember, they're not used up in the reaction. Now, when I talk about an alternative pathway, we have an energy diagram where we have the reactants and the products. We have what's called an activation energy hump. There is a certain amount of energy I need to have in order for the reaction to be successful or to start. But if I have an alternative pathway, it has a lower activation energy. Now, that's important because we need to state both of those phrases, that the catalyst provides an alternative pathway with a lower activation energy. So we need to get that sentence with those two phrases in the first instance. Then we say, therefore, more of the particles will have enough kinetic energy to overcome the activation energy. Remember, why will more particles have the kinetic energy to overcome the activation energy? Because we made the activation energy lower by providing an alternative pathway by providing the catalyst. This will result and an increase in the rate of reaction. We can just write that at the end to link it to the context. And those are the four things, okay? So we have concentration, temperature, surface area, and catalyst. And you need to be prepared to write a paragraph explaining, well, in the first instance, identify in the question which one of those four factors are going to be relevant to the question. Usually you can see whether it's a concentration because they'll state that there are different concentrations, or surface area they'll say there's a powder and there's a solid piece. With a temperature, they will tell you that this reaction happened at this temperature and then this one happened at a different temperature. And with catalysts, it will usually just be they've added some substance to the reaction, and because of that it went faster. You then go, oh, that's a catalyst. So you need to identify each one of those four and then explain using the phrases I've just gone over. Okay, so the next section that we're going to look at in this reactivity standard is equilibrium. Okay, so equilibrium, often we call it dynamic equilibrium, and the reason we call it dynamic equilibrium is because the reactions, well, we'll talk about this in a second. So for most chemical reactions, we think that we add two things together and two reactants and they produce a product, right? And that all of the reactants have been turned into product. However, that's not always true. So here's an example. If I took a glass of water and I put it onto the windowsill, now eventually what will happen is all the water will evaporate. So what's happening is we have this liquid water turning into water in the gas phase. Okay, so are you happy? Now if I took that same glass but I put a lid on top and left it in a warm place, the water would start to condense on the side, right? So you get all these wee droplets of water condensing on the side. So what's happened there is actually the water is the gas vapor is turning back into liquid water on the side of the container. Now in that environment, so we're imagining a glass of water with a lid sitting on a windowsill, okay? We have two reactions happening at the same time. We have a liquid turning into a gas and a gas turning into a liquid. These two are opposite reactions. They are at dynamic equilibrium. Now what we mean by dynamic equilibrium is that at some stage, sitting there in the sun, the water isn't going to go anywhere because there's a lid on it, but the amount of water that is turning into a gas is going to be equal to the amount of gas that's turning into a water. The rates that they are reacting are at the same rate, right? So these reactions are said to be at dynamic equilibrium. We often just use the word at equilibrium, that's fine, but what it means is there is some water in the liquid phase and some water in the gas phase. There's actually a lot more liquid water than gas water, but that doesn't influence the equilibrium. But when we say something's at equilibrium, we mean that the forwards reaction is happening at the same rate as the backwards reaction. And we represent this by drawing an arrow that goes forwards with an arrow that goes backwards underneath it. And the arrows are of similar size because it's at dynamic equilibrium. Both reactions are happening at the same rate, the forwards one and the reverse one. So let's go on to the next slide. So equilibrium expression. So for a general equation, we have this equilibrium expression given here. Okay, so you would have recognized, you would have seen this, and we need to remember this generally how this works. So this on the left hand side, this equation represents a reaction, with the little letters being the coefficients and the large letters being the substance, right? When we write an expression, we rearrange how we draw this into a mathematical equation, and we draw it by writing K equals the products. We put the products on the top over the reactants. Now the products have to be written in a certain way. The substance has to be, we have to put a square bracket around the substance, and then its coefficient has to be written as an exponent. Now, what do I mean by that? Well, let's look at an example here. So here's an example of carbon reacting with two waters to produce two hydrogens plus carbon dioxide. Now notice that here my products that I'm going to write on the top, because the products are already right on the top, there are two of them, so I'm going to write this expression. So the H2 will go to the top and the CO2 will go to the top. They will be encased in square brackets, each one. And the H2, because it has a coefficient in front of it, and its coefficient is 2, I'm going to write it as an exponent above H2. And that there is of this fraction that I'm going to use for my equilibrium constant. That's the top part of the fraction done. Then I do the bottom part. So here's the two species I'm going to put on the bottom. There's the carbon, there's the water. I'm going to put them in square brackets, and because the water has a coefficient of 2, I'm going to write that at the top. Now, you might get to a situation where you don't have 4 terms, you just have 3 terms. That's fine. If you don't have a D, then you don't put a D there. So if it was just carbon plus water made carbon dioxide, there was no hydrogen, right? You would just put 1 term on the top. So you use the equation to guide you, but knowing if there are products, they go on the top. Each term that is separated by a plus sign is in its own square brackets, and the coefficient goes as the exponent at the top. Now, between these actual terms that we put into the equilibrium expression, there's an actually multiplication happening here. Take care that you don't just by habit put an addition sign, right? You can either put a multiplication sign or just leave it, because in maths, if we don't have a sign there, we assume that it's multiplying. Interesting, the square brackets actually mean something in chemistry. They mean it's the concentration in moles per litre of that substance. So what we've essentially done here is we've written the term by putting the products in square brackets over the reactants in square brackets. That's the equilibrium expression. Right, so once we've done the equilibrium expression, we can calculate K. So here's an example. If H2 has a concentration of 0.1 moles per litre and iodine, I2, has a concentration of 0.033 moles per litre, HI has the concentration of 0.55 moles per litre. What is the Kc, or the K in this? Sometimes we'll use the term Kc. What is the K in this situation? So I draw my expression. I put my products, which is, there's just one product in this. So even though we have that A plus BB equals CC plus CC, I'm only using the C here. So I've got HI exponent 2, and then at the bottom I've got H2, and I've got I2, right? So that's my expression. So I write my expression, and then I substitute. So I see H2 has the value of 0.15. So I put that in here, 0.15 on the bottom where H2 is, and then I have 0.33 on the bottom. Now I've put in the units here. You don't have to put the units when you substitute them in. You don't have to put their phases as well. See up here that I wrote that they were gases. You don't have to put that in the expression. The expression is just so you can do the math here. So I've substituted all the values with their numerical values from the question, and then I solve it. Now, if I'm working out the value for K or Kc, it does not have a unit. Okay, so here at 61.1, I don't have to put a unit here. So this is one of the rare situations that you don't have to put a unit in the chemistry calculations. Okay, so here's another problem here. So in this case, we're told that there is 0.23 moles of H2, 0.00456 moles per litre of NH3. They say that the following equation is at equilibrium at 470 degrees Celsius, and that the Kc is at 473 is 0.15. Okay, so we're told the equilibrium constant, and we're told 2 concentrations. But what we're not told here, we're told the concentration of hydrogen and the concentration of ammonia, but we're not told the concentration of nitrogen. That makes sense because they're asking us what is the concentration of nitrogen. First step, we're going to draw the Kc expression. Here it is. Second step, we're going to substitute the values we have. Now, don't be confused that they have told you what the temperature that the equilibrium constant is at. The reason they do that is the equilibrium constant value is only valid for a specific temperature. So they have to state what the temperature is. So if you see the temperature, you just ignore it, right? So they've told you the temperature, but they've told us the constant at 0.15. We're going to put it in where the Kc is. And we're going to put the other values in where they go. Okay, so we put the expression in here. We've now substituted, and I need to rearrange and solve. You can put it into equation solver in your calculator. You can rearrange it. The quick, easy way to rearrange things is I'm going to anything. If I have something on the bottom of the fraction on one side and something on the other side by itself, I can just actually swap those two positions mathematically. We could go through a whole proof to show how we do that, but I'm not going to at the moment. So I'm just going to rearrange this. So N2, now see how I swap the N2 and the 105? That's a valid swap there. So I do that and then I solve and I get an answer of 0.0163 moles per litre. In this case, I do have to put a unit. So anytime that you're giving the value of a concentration, and that's, I'll know that because there's a square bracket, it's going to be moles per litre. But if you're giving the value of a K or a Kc, it's going to have no unit. Okay, so let's calculate the concentration of this situation. So I have 0.4 moles per litre of nitrogen and 0.65 moles per litre of hydrogen. They're present in this equation here. Again, they've told us, hey, there's a Kc, it's 105, it's at the same temperature we had before, which is 473. That's the temperature it's stated for. But in this case, they want us to find the concentration of ammonia. That's the unknown. Okay, so first thing we're going to do is write the Kc expression. Okay, so you can see here that the ammonia is going to be the unknown, but in this case, what makes this problem harder is the ammonia has an exponent. It's squared. Okay, so we're going to resolve that at the last bit of this solution. So I've written a Kc. Remember, the next bit is we're going to substitute, we rearrange, and then we solve. So I substitute in the values. So I've put the K in the left-hand side, and I've put the concentration of the ammonia, and the ignore the square brackets there. Once I've put the numbers in, I don't need the square brackets. I've just put normal brackets in there. I actually don't need the normal brackets, but that's fine. I'm going to rearrange this. So how did I rearrange this? Well, because if I multiply both sides by 0.4 and 0.65, the bottom terms would cancel and we would get ammonia squared equals these three terms. So here's the value for ammonia squared. Be careful. There are so many students who will leave this as their answer. This is not their answer. This is the answer for ammonia squared. So now we actually have to get the ammonia answer for the concentration of ammonia. So we square root both sides. So the concentration of ammonia is the square root of this answer, which is 107 moles per litre. Moles per litre because it's in square brackets and must be concentration. That there is our answer. Okay, next part. Okay, so magnitude of K. So the K just represents, the K value represents, remember, a ratio of products over reactants. So K is how many products over how many reactants. It's a fraction of products over reactants, but it gives us a whole number. Well, not a whole number, it gives us a number, right? So here's an example of a reaction. So you can see that we have less reactants than we do products, and we can see it's at dynamic equilibrium because I've represented the forwards arrow being the same size as the reverse arrow. In this case, because the product is larger than the reactants and K equals products over reactants, we're going to have a number that's larger than 1. Okay, so we're happy with that. So what we're going to be looking at soon is how do we impact the equilibrium? So what if I added more of the reactants? If I added more of the reactants, then what's going to happen is the reaction will oppose the change and try to restore itself to the equilibrium it had. Now the equilibrium it had is the ratio of products to reactants. In this case, the products are about 3 times larger than reactants. I added some more reactants, but now the reaction is going to favor the forward reaction, Okay, this equilibrium is going to favor the forwards reaction to return to the same ratio, the same magnitude of K. So the ratio then returns back to equilibrium. Now, yes, we have more products and we have more reactants, but the ratio is still 3 to 1. We still have the same ratio of products to reactants. And that's all that happens in an equilibrium. Whenever we make a change to an equilibrium, it will oppose that change to take it back to the original position of equilibrium. And when we're talking about position of equilibrium, we're saying the ratio of products to reactants. And that is shown by the value K. The value K, remember, products over reactants. So an example of this, okay, so if K has if the equation has lots of products and hardly any reactants, we're going to get a very large number of K. In this case, 100 products is the concentration and 1 is the reactant concentration. So the overall concentration is 100. That's a very large number. That means, so if we ever see a large number for K, we know there are lots of products and there are few reactants. However, the opposite is true. If we only have a small number of products and a large number of reactants, we get a very small number. So if we see a very small number, we're going to recognize that there aren't very many reactants in the reaction equilibrium. So here's a summary of this. So we have really 5 positions. We have 1. If we have a K of 1, because this is a fraction, we have equal amounts of products and reactants. And we say the position, okay? And if we have a number that's bigger than 1, we say there are more products and reactants. So if we have a really large number, we can say, well, the reaction's almost gone to completion because there are hardly any reactants left. Opposite is true. If we have a number less than 1, we have more reactants than products. If we have an incredibly small number, we say, well, we don't have many products. It most probably didn't react. Okay. Right, Le Chatelier's principle. We just talked about Le Chatelier's principle 2 slides back, but we didn't call it that. So Le Chatelier's principle is, when we have a system at dynamic equilibrium, if we make a change to that system, it will react to that change to get back to the original equilibrium. So if we think of those piles that I had in that diagram, they want to get back to the same ratio of products and reactants. So we can change the a reaction equilibrium. We can make changes to it we can change the temperature, we can change the pressure, we can change the concentration. We can also change the amount of product or reactant we add. So there's kind of like 4 things that we might have to talk about. But remember, if it's at dynamic equilibrium, if it's subject to a change, if a change happens, it will react to do the opposite, to lessen the change. Here's an example. So an example here is concentration. So here, I'm adding some thiocyanate to a reaction. So there's a reaction that's happening here. This is iron and thiocyanate are at equilibrium with this iron thiocyanate complex, right? So this is a reaction at dynamic equilibrium. So this solution is already at dynamic equilibrium. It has these 3 particles in it. The 2 reactants are forming the products, and the products are breaking apart to form the reactants. And the forwards and the reverse reaction are happening at the same rate. Well, what happens is, what if I added some potassium thiocyanate, which is essentially just thiocyanate plus potassium? If I added those 2 things, then what I'm introducing is more of this SCN- to the reaction. Now, remember Le Chatelier's principle. If I make a change, the equilibrium will move to oppose that change. Now, how this works, let's have a look. So if I add some more SCN-, and I did that by adding potassium SCN, right, then what's going to happen is the solution is going to go more red. Now, because it went a darker red, it's indicated that more iron thiocyanate is being made. So what does that mean? The forwards reaction must have been favoured, but that makes sense. So here's what we need to remember here. If more reactants are added, Le Chatelier's principle says that the system will act to oppose this. If I add more SCN-, the system will oppose this change. In this case, the Ford's reaction will be favoured because the Ford's reaction will use up the SCN minus that's been added. Now, because the Ford's reaction has been favoured, more Fe SCN2 plus has been made, and therefore the solution becomes more intense blood red. Now, the Ford's reaction will only be favoured until a point that the ratio, that's the K, is established again after you've added. So initially you add more reactant, it's imbalanced, the Ford reaction happens until it's balanced again. So we can also change the concentration in the following way. So in this case, I'm adding some sodium fluoride. Now, what you need to know is that the fluoride will react with iron 3+ and turn it into a different species. So it's essentially removing the iron from the equation. Okay, so if I have this reaction at dynamic equilibrium again, we're removing the iron. Now remember Le Chatelier's principle, it says that the equilibrium will move to oppose this change. So the equilibrium is going to want to make more iron to replace the iron I took away. So the reverse reaction is going to be favoured in this case. And if the reverse reaction is favoured, there's going to be less blood red and more orange colour. So if some reactants, in this case Fe3+ are removed, the equilibrium will favour the reverse reaction to replace the reactants lost. The concentration of iron thiocyanide will decrease and the blood red colour will disappear. I shouldn't have said disappear there, I should have said becomes less intense or becomes less red. It's not disappearing, there's still going to be some, right? Here's an example. Okay, so imagine if I had nitrogen gas and oxygen gas, both colourless, they react together to produce this brown NO2, nitrogen dioxide. Explain what effect removing NO2 would have on the reaction, would have on the yield of the reaction. Okay, so yield is an important term that they might use. Yield is how much overall total product would be made. Now, so if we remove the NH2, what do you think the equilibrium would do to oppose it? That's correct. What it would do is that if you remove the NH2, is the Ford's reaction would be favoured in order to produce more NO2 to replace what we have lost. So if you remove the NH2, it would make more NH2. Overall, there would be more NH2 produced and we would have a larger yield. So when NO2 is removed, the concentration NO2 decreases. The system will oppose this change by favouring the Ford's reaction. More reactants will be used up to produce more products. So overall, more product will be made, producing a larger yield. That's the concept of yield and how it's applied to concentration here. Okay, change in pressure. So we can change the pressure in the situation. So here's an example of two gases that react together. We've got nitrogen dioxide again and N2O4. In this situation, there is a low pressure and a large volume. Okay, so if I write the equilibrium expression, I have this expression here, which is 2 NO2s goes to N2O4. Now, if the pressure increases, the equilibrium will move to the direction with the less gas particles. So how do I increase the pressure? I decrease the volume. If I decrease the volume, there is now more pressure on the solution. Now, in this case, what's important is how many particles are on either side. There are 2 gas particles on the left side of the equation, and there is 1 on the right. And if I increase the pressure, the equilibrium, the direction that will be favoured, the Ford's direction will be favoured because it is moving towards the side with the less gas particles. Increase the temperature, we move to the side with the less gas particles. Okay, here's an example of a concentration question you might get. So the same one we just kind of looked at. Oh no, it's a different equation actually. So nitrogen gas and oxygen, both colourless, react together to produce brown nitrogen dioxide gas. Explain what you would observe if the volume of the container of the reaction taking place was decreased. Now I just have to say that the volume of the container decreasing increases the pressure. You need to be aware of that. They're usually not going to phrase it in that way. They're usually just going to say that the pressure increased. So the pressure is increasing. What's going to happen here? So in the first instance, when we explain these situations, we're going to say how many moles of gas particles on the reactant side and how many moles are on the product side. Once we've said that, we're going to say the statement that if we increase the pressure, we will move towards the side with the least gas particles. And then we're going to resolve those 2 points, and we're going to say what happens. So there are 3 moles of gas on the reactant side and 2 on the product side. When the volume is decreased, the pressure increases. Okay, so that's resolving that bit about the volume and pressure. When the pressure increases, the system will act to oppose this change, and the Ford's reaction is favoured. Now, I always like to advise people to put the phrase that the system will oppose the change. That's Le Chatelier's principle included in your statement. So we're saying the Ford's reaction is favoured, and that because that is the direction that favours the less gas particles. And remember, because we increased the pressure. If more NO2 will be produced, the colour will be darker brown, because they told us the NO2 is brown. So we are relating what the result is to the context here. They asked us what would the colour change, what you would observe. So we observed that it would be a darker brown colour. And notice we've got quite a comprehensive explanation for this. Okay, so now let's look at how temperature might affect equilibrium. Okay, so here is an example of a equation at equilibrium. In this equation at equilibrium, we're given a delta RH, or an enthalpy value for the reaction, and notice that it has a positive. Now, they're usually going to write a positive sign. If they don't put a positive sign and there's no negative sign, it's still going to be positive. So this is a positive value, and this means this reaction here is endothermic, right? Now, what it means by it's endothermic, the value that's stated for the enthalpy is always stated for the Ford's reaction. So the Ford's reaction must be endothermic because the delta R value is positive. That means that the opposite is true for the reverse reaction. The reverse reaction is exothermic. Now remember, endothermic reactions remove heat, and exothermic reactions give out heat or release heat. So what happens when I change the temperature? If I increase the temperature in this situation, remember Le Chatelier's principle, it wants to oppose the change. If I try and heat up something, then the reaction is going to try and cool it down. How is it going to cool it down? It's going to cool it down by going in the endothermic direction. So if the temperature increases, the equilibrium will move in the direction to remove the heat, the endothermic direction. If the temperature decreases, obviously the opposite's true. It's going to go in the exothermic direction and add heat. So here's an example here. So nitrogen gas and oxygen gas, both colourless, react together to produce a brown nitrogen dioxide gas. Explain what you'd observe when the reaction was heated up. Now, notice here that I haven't put a positive in here, but because there's no negative and we know this is a positive number, therefore this is endothermic. Now when I say this is endothermic, I'm talking about the Ford's reaction is endothermic. And remove the heat. As the reaction is heated up, then the reaction will move to oppose this change by moving in the endothermic direction, right? So the Ford's direction will be favoured and more NO2 will be produced, producing a darker colour. So I would advise actually is that you write above the arrow endothermic. So once you've resolved the enthalpy change here and you work out that it's endothermic or exothermic, you write it above the arrow, which one it is. So in this case it will be endothermic above the arrow and I write exothermic below it. Just helps me when I'm writing my paragraph. Okay, so magnitude of K. So this is kind of the last point, but the hardest question here. So what would happen to K if the temperature is increased in the following reaction? So the magnitude, the value of K is constant apart from when we change the temperature. Now, we don't need to go into the details of this, but if we change the pressure, the K stays the same. If we change the concentration, the K stays the same. If we change the the temperature, then the K will change. The K is only constant for a given temperature. Now here they want to know what will happen to K if the temperature is increased in this reaction. So we have to go through a few steps to see what would happen. So in the first instance, we can note that this reaction, the Ford's reaction, is endothermic. Good to know. That means the reverse one is exothermic. The endothermic reaction will be favoured because it wants to oppose increase in temperature. That makes sense. If I've increased the temperature in this reaction, it's going to want to cool it down so it goes in the endothermic direction. So this is the Ford's direction. The Ford's direction is favoured. But then because the Ford's direction is favoured, we increase the concentration of the products while the concentration of the reactants decreases. Now remember, we had this fraction, K equals products over reactants. If we made more products and less reactants, then the value of K will get larger. So when we increase the temperature, the value of K will get larger. So this is quite an in-depth explanation of what happens to K when we change the temperature, and it is going to be the most challenging question in this part of the paper. Okay, so let's go and look at the acid-base part of it. Okay, let's look at the acids and bases component of this paper. Okay, so generally we have acids taste sour, they turn litmus paper red, turn universal indicator red, oranges or yellow possibly as well, and they react with metals and carbonates. Bases taste bitter if you're tasting them, turn blue, litmus blue and universal indicator blue. They feel soapy if you put them on your hands, and they neutralize acids. So those are just general properties we might know about acids and bases. Now we have two important definitions of acids and bases. We have one called the Bronsted definition of an acid. Now the Bronsted definition of an acid is a substance that donates a proton. And because of that, a base is a substance that accepts a proton. So in this case, in this example here, we have the acid is HA. It donates a proton to the base, and the acid then becomes deprotonated. It loses a proton and a positive charge, and the base gains a proton and a positive charge. That is a definition of a Bronsted acid and base. Arrhenius definition of an acid, so is another way of looking at it, is an acid is something that when you put it in water produces H3O+. So you could use either explanation to say something's an acid. So if I put HCl in water, it will react with water to produce H2O+, therefore it is an acid. Also, if I look carefully at HCl, I can see it donated a proton to water, so I could say it's an acid from Bronsted definition. A base is something that when we put it in water, that it produces OH minuses. So we have ammonia here, it's reacting with water, it's producing an OH minus. Any solution, so remember in any solution there's already OH minus and H2O plus present. If we know the concentration of one, we can work out the concentration of the other. We'll go over that later. And we can use this expression here. This is the equilibrium constant for water. Okay, so how do we calculate the pH? So remember, acids and bases have this value called pH that tells us how much of an acid and a base. If it's up near 13, 14, it's a strong base. If it's down near 1 or 2, it's a strong acid. But we have a scale between 1 to 14, and we can actually carry out a calculation to work out where a strong acid or base is on that scale. So if a pH has a low number, it tells us there's lots of H3O pluses in the solution. If it has a high number, it tells us there's lots of OH minuses in the solution. So here is some different concentrations of an acid of H3O plus, and here is the pH. So how did I work out the pH from the concentration of H3O plus? I use this equation. And this equation is on your resource sheet, and it's the pH equals negative log H3O plus. So essentially what we do is we put the concentration, we press log, we put the concentration in and we press execute on our calculator, and it gives us a number. The number is always going to be negative because the exponent for the H2O plus is negative, so we put the wee negative sign in front to make it a positive number. So a solution is found to have a concentration of 0.0045 moles per litre H2O plus. Calculate the pH. pH equals the log of 0.0045, right? 455. You put that into your calculator, you solve, you get an answer, pH 3.4. pH does not have a unit. This is an achieved question. It will always be in the paper, and they expect you to have practiced doing this on your calculator. Make sure you are familiar with the buttons you use to calculate the pH on your calculator and practice it. Okay, so we've seen there that we can calculate the pH, but actually if we know the pH, we can calculate how much H2O plus is present. So we can use this expression that's also on our resource sheet. The H2O plus equals 10 to the negative pH. Now, 10 to the negative is actually the inverse log button. You press shift log or second function log on your calculator. So if a solution has a pH of 5.6, what is the hydronium ion, H2O plus ion concentration? We put we substitute into this equation and we solve using our calculator. Now again, on your calculator, you're just going to put inverse second function log, and then you can put number minus 5.6, and it will give you back the answer. Now it won't necessarily give you the answer in standard form. It depends how you set up your calculator to display. My students mostly are more comfortable with using it in just general form, so that would display as 0.00000251. So you have to be comfortable whatever form you want to represent your numbers in, but I prefer standard form when I do it on the calculator. Okay, so if I want to calculate the pH of a strong acid, so if they said, okay, we have this concentration of the strong acid, nitric acid. The first thing I need to do is I need to make an assumption. Because I know this is a strong acid, I know that it's going to react with water to produce H2O+. Therefore, notice every one of my strong acid particles produces one H2O+ particle. These ratio of moles are equal, so therefore, and it is equal because it's fully dissociated, therefore the concentration of H2O+ is just equal to the concentration of the acid. So you might automatically make that assumption, but you should state it. You should say that the H2O+ is equal to the concentration of the acid, and then we substitute into the equation. We do log of the number, or negative log of the number, and we get the answer of 1.6. So that's how we work out the pH of a strong acid. You can't actually calculate the pH of a weak acid at this stage. That's something we learn at level 3, but we don't do at level 2. Okay, if we know the pH, can we calculate the concentration of the strong acid? Yes, we can. So calculate the concentration of hydrochloric acid, strong acid, right, with a pH of 3.7. So remember again, we're going to use the second function or inverse log, second function log, to calculate the H2O+ concentration for pH in our calculator. So we're going to put that value into our calculator. We're going to get an answer which is 0.002 moles per litre, but that's the concentration of H2O+. They wanted the concentration of the acid. Well, we just need to know in the back of our head that the HCl reacts, has a fully reacts with the H2. Okay, so it fully dissociates. So the concentration of HCl plus is equal to the concentration of H2O plus. So the concentration of HCl is the same, 0.00200 moles per litre. Now, you will normally just do that, but you need to think about what you're doing in case they ask you a question around this. What if you have to calculate the pH of a strong base? Well, a strong base is slightly different, right? So a strong base doesn't produce a high concentration of H3O plus ions, it produces a high concentration of OH minus ions. So we need to use a different expression to resolve this, and this is the equilibrium constant for water. And this is the equation. I've rearranged it here, but actually the equation you'll be given is Kw equals H2O plus, the concentration of H2O plus times the concentration of OH minus equals 1 times 10 to the negative 14. So the first thing I do is I'm going to do the dissociation of sodium hydroxide. Now when I look at a strong base, I always put the water above the arrow. Okay, and basically this is an ionic lattice. It breaks into sodium ions and hydroxide ions. Hydroxide ions are what give it the property of being a strong base. For every 1 mole of base produced, of OH produced, every 1 mole of base produces 1 mole of OH minus. So the concentration of OH minus is 0.0300, same concentration as the base. Cool, that's fine. But in order to calculate the pH, I can't use the OH value, okay, because the pH is a log of the H2O plus concentration. So I need to convert or to find out the H2O plus concentration when I know the OH concentration, and that's where I use this expression here. And if I want to find out the hydronium ion concentration, the H2O plus concentration, I'm always going to divide 1 times 10 to the negative 14 divided by the concentration of the hydroxide or the base. So it's always 1 times 10 to the negative 14 divided by. In fact, if I want to find out the concentration of the base and I know the hydronium ion, I also need to divide 1 times 10 to the negative 14 by that. It's the same every time. So I put that into this expression and I solve, and I get an answer of 3.33 times 10 to the negative 13. I haven't finished yet though. I need to resolve this by calculating the pH. I put that into my calculator and I get an answer of 12.48, and I go, yes, that's amazing, because it's a high value. It's close to 12, 13, 14. That is what I would expect from a strong base. I must have done my answer I must have done my answer correctly. Well done. Let's move on. So if we want to calculate the concentration from pH of a base solution, it's one more step than if we want to do that from an acid solution. So here's an example. If I have potassium hydroxide solution with a pH of 12.5 and I want to calculate the concentration of the potassium hydroxide solution, I'm going to first have to find out what the concentration of H2O plus is, because if I have pH and I put this into the equation on the top right here, okay, the only thing that I can work out is H2O plus concentration, but that isn't going to tell me the concentration of the potassium hydroxide. I need to find the concentration of the OH. But I use the second equation here to find the concentration of the OH once I've worked out the H2O plus concentration. So first step, work out the concentration of H2O plus from the pH. So I work that out by putting that in my calculator. I go negative log 12.5 and I get 3.16 times 10 to the negative 13. Now that is the concentration of H2O plus. And remember, the equilibrium constant of water says the concentration of H2O plus times the concentration of OH minus equals 1 times 10 to the negative 14. So if I want to find the concentration of OH minus, I divide 1 times 10 to the negative 14 by this number, and I get 0.0316 moles per litre. So the concentration of the hydroxide ion is this, but because 1 mole of potassium hydroxide produces 1 mole of hydroxide ion, this is also the concentration of potassium hydroxide, and that's how we work it out. But remember, when we want to work out the either the base or the the pH or the concentration of a base, we're going to have to use the equilibrium expression or constant expression for water. Okay, we're going to have to use this 1 times 10 to the negative 14 equals H2O plus times OH minus to change the concentration of OH minus into H3 plus, or change H2O plus into OH minus. Okay, so just as an aside, equilibrium constant of water, where does it come from? Well, actually, if you have a container of water, the water molecules will actually zip around and collide with each other, and when they do that, they produce hydronium ions and hydroxide ions. So there is a proton exchange between it. Now, because two water molecules produce a hydronium and hydroxide, every time we produce an H2O plus, we produce an OH minus. So water always has the same concentration of H2O plus as OH minus. It is neutral, but it does have acid ions and it does have base ions. It has them in equal concentrations. Now, the concentration of each of those ions is 1 times 10 to the negative 7, right? Because Kw equals 1 times 10 to the negative 14, that means OH minus must be 1 times 10 to the negative 7. H2O plus must be 1 times 10 to the negative 7. So 7 times 7, exponent 7, 1 times 10 to the negative 7 times 1 times 10 to the negative 7 equals 1 times 10 to the negative 14. Now, the number 1 times 10 to the negative 7 is important because if that is the concentration of H2O plus and I put that in to work out the pH, it's going to give me a pH of 7 because the pH is just an expression of what the negative exponent is of the concentration. Okay, so this is most important though, and that is this expression, 1 times 10 to the negative 14 equals OH minus times H2O plus. Remember, you're going to use this when you want to work out the concentration of OH minus, when you know H2O plus, or you know H2O plus and you want to find the concentration of OH minus. And practically what it is, if you want to find one from the other, you're always just dividing 1 times 10 to the negative 14 by the value that you have. Okay, what are conjugate acids and bases? So we've said that the Bronsted definition of an acid is it donates a proton and a base accepts a proton, right? So in this case, if we look at this equation, we can see that of the two reactants, one of them is going to be an acid, one's going to be a base. Now, if we look here, we can see that the hydrogen fluoride becomes a fluoride ion, so it must have lost a hydrogen, a proton, an H+. It actually donates the proton to water, and you can see that the water has gained the proton as we go across the reaction. It's become H2O+. Because hydrogen fluoride has donated a proton, this here is an acid, right? Because water is accepting a proton, because this hydrogen fluoride, once it's donated its acid, turns into the fluoride ion. The fluoride ion is called the conjugate base of the acid, or this is an acid and this is its base pair. This is an acid-base pair. If H2O is a base because it's accepting a proton, but its conjugate acid is H2O+, because that's what it became after it accepted the proton. So another thing to notice is that on either side of the equation, when we do acid-base reactions, we always have an acid and a base, but we also should be able to have a pair of acid and bases, one from either side, and they are similar, but the only difference is one has the hydrogen where the other one has one more hydrogen and positive charge than the other. That is our acid-base pair, and the one of those pair that is the acid is the one with the more hydrogens. So a conjugate base is produced from an acid, and so let's have a look here. Here's a whole bunch of acids. What would its conjugate bases look like? Well, if I want to work out what the conjugate base is from the acid, I remove a hydrogen and I remove a positive charge. So HC2O3 becomes C2O3 minus. NH4 plus loses a hydrogen, NH3, no charge because it lost a positive charge. HSO4 minus becomes SO4 minus, it lost a hydrogen and it lost a positive charge, it got one more negative, and CH3COOH becomes CH3COO minus. A conjugate acid is produced after a base has produced a proton. So if I have a base and its conjugate acid, in this case it's accepting a proton, so it gets one more hydrogen and one more positive charge. So in the first case we have HCO3, it's going to become H2CO3. Okay, no charge because the positive cancelled the negative. If we add the hydrogen or the proton to H2O, it becomes H3O plus. If we add it to HPO4 minus, that becomes one more positive and one more hydrogen, H2PO4 minus. And if we add it to CH3NH2, one more proton, it goes to the ammonia side, so it's NH3 plus. And that's conjugate acids and bases. Now, conjugate pairs. So we talked about that in the previous one. You can identify the acid-base pairs. Remember, the two species that are similar and different by just a hydrogen and a positive charge. So here we can see that these two, the acid and the base, are similar. The only difference is the acid has one more hydrogen and one more positive charge. This is an acid-base pair. The other acid-base pair is the hydronium ion is the acid and water is the base. If they ask you in the question to write down the acid-base pairs, make sure you put them in the correct order. If they've given the expression acid/base, then you write the acid first. So the first acid-base pair would be HCO3 minus, CO3 minus, and the second one, we write the acid first, H3O plus / H2O. What's the acid-base pair of the next one? Well, we can see NH3 is an NH4, so NH3 must be a base, NH4 plus must be the acid, right? And we can see H2O, OH minus, H2O has the extra hydrogen, it's the acid, OH minus is the base. And then we represent these around the correct way, right? So NH4, if we're doing acid-base pairs, it's NH4 plus, NH3 minus, H2O / OH minus. Okay, strong acid. Let's just look at what an actual strong acid does and explain why it has a low pH and why they conduct electricity well. So the most important thing, if you have to write an explanation about strong acids, is you put the following term in. They fully dissociate in water. What that means is we draw an equation for them reacting with water, and we must draw a solid arrow pointing towards the right-hand side. So a strong acid reacts with water to produce a hydronium ion, and it produces also an ion, another ion, and so hydrochloric acid will produce chloride, right? So we have an acid, the conjugate base. This in a strong acid, the Cl minus is neutral, so any ion that is produced from the strong acid, not the hydronium ion, but any other ion, is said to be neutral. And the reason it's neutral is this reaction went completely to the right hand side. It means that the Cl minus, even though we call it a conjugate base, it won't go back and go back the other way and act as a base. So it's actually a neutral. And actually the ions that are produced from strong acids, right? So they are always neutral. The salts produced from strong acids are neutral. So hydrochloric acid produces chloride, it's neutral. Sulfuric acid produces sulfate, it's neutral. Nitric acid produces nitrate, it's neutral. Those ions are not weak bases. So any conjugate base produced from a strong acid is not a weak base. So when a substance fully dissociated, the concentration of its products is equal to the concentration of the reactant. So if I had 2 moles per litre of HCl, I would have 2 moles per litre of H2O plus and 2 moles per litre of Cl minus. So what that means in essence is I can just assume that the concentration of hydronium ions is the same as the concentration of acid. I can also assume that there is a high concentration of ions, so it will conduct electricity really well. You need to remember the following 4 strong acids for this assessment: hydrochloric acid, HCl, hydrobromic acid, HBr, nitric acid, HNO3, and sulfuric acid, H2SO4. You need to be able to draw the reaction for each of them, which is pretty straightforward. They always produce a hydronium ion, they're always reacting with water, and they produce an ion as well, a negative ion. And remember that negative ion is always neutral. A negative ion produced from a strong acid is always a neutral substance. And let's have a look at our next slide. Okay, so what about strong bases, you ask me? Well, strong bases are a different matter than strong acids. So they do fully dissociate in water, but we always write the equation differently, right? So if you remember back to 2.4, water is a polar molecule, right? It has a positive side and a negative side. The positive dipole is the side with the hydrogens, and the negative is the side with the oxygen. But sodium hydroxide, when we drew show it fully dissociated in water, we don't add water, we just write water above the arrow, and we say that it separates into sodium ions and hydroxide ions. Now, why is this so? Well, the reason that it's so is actually sodium hydroxide is an ionic lattice, right? It's made up of alternating sodium and hydroxide ions. And it's actually, when it dissolves in water, it's pulled apart by water molecules. Remember, the water molecules form an attraction to the ion, the opposite polar side forms an attraction to the ion that is just as strong as the ions had for each other, so it dissolves. Now, the water actually itself isn't changing, but what we're doing is we're adding more OH minuses to the solution. So the OH minus is not coming from the water donating its proton, it's coming from the actual ionic lattice, right? So this is a strong acid, it just produces lots of OH minus, which is why we put the water on top, because we're putting it in water. So it ends up like this, right? So that's why we draw the arrow a wee bit different. So it's with strong acids, weak acids, and weak bases, we're always adding water, and we're always using the Bronsted definition, proton donor, proton acceptor. And this situation, this is Arrhenius's definition of an acid and a base. It's a base because it produces lots of OH minus. The OH minus comes from the solid just breaking apart this ionic solid into its particles, the OH minus and sodium pluses. So the strong bases we need to be familiar with are basically any bases from either the first column in the periodic table or the second column metals. So sodium hydroxide, potassium hydroxide, calcium hydroxide, right? We could have lithium hydroxide as well. I didn't put that there, but any of those things, if you find it if they're from group 1 and group 2 and hydroxide, they're going to be strong acids. What about weak acids? Strong bases, sorry, weak acids. Okay, weak acids. When we talk about weak acids or weak bases, we're always going to use the phrase partially dissociate. Strong, fully dissociate, but in this case, weak acids partially dissociate. Now, partial dissociation means we have an equilibrium arrow in a reaction. So our weak acid is reacting with water, and it's acting as a Bronsted acid, right? It's donating its proton, so we produce its conjugate base that has one less proton and one less hydrogen, and water has accepted the proton and it produces a hydronium ion. Okay, so this is classic acid definition, how an acid works. It both donates a proton and it produces an H3O plus. When the substance partially dissociates, and what that means is it doesn't mean that at one instance it partially does. It means if we had lots of them happening, there's only a small fraction of the products compared to the reactants. So the equilibrium is set up, but it's very heavily, there's a lot more reactants than there are products. So there's not very many products at all. There's some, and there's definitely a dynamic equilibrium, but the concentration of the products is usually 1,000 times smaller than the concentration of the reactants, right? So there's not many products. The type of weak acids that we need to be comfortable to remember are ethanoic acid, methanoic acid, and ammonium ion. Also, the other weak acid would be hydrogen fluoride and possibly amines, right? Hydrogen fluoride is HF. Amines are organic molecules that have NH2s attached. Remember, they partially dissociate. They have an equilibrium arrow. They do produce hydronium ions. And the interesting thing about this is, yes, they do produce a conjugate base, but actually the base of a weak acid is itself a weak base. So this is a weak acid, but NH3 is a weak base. So that's an interesting thing about weak bases and weak acid. Their conjugate acid or base is also weak as well. Okay, so weak bases, similar to weak acids, apart from instead of producing hydronium ions, they produce hydroxide ions. They partially dissociate in water. So this is the phrase we're going to use when we explain them. So you should see that the weak base will accept a proton. and become a species that has one more hydrogen and one more positive charge. The water that is reacting with it, of course, will donate its proton, so it will become hydroxide ion. The common weak bases that we might encounter are carbonate ions, ammonia, and amines. So amines are weak bases. I might have mistakenly said that they're weak acids in the previous part of this video, but they are definitely weak bases, right? So these, now amines, it could be CH3NH2, it could be CH3CH2NH3, but any type of amine is a weak base. There's actually the fluoride ion is a weak base as well, because it's a conjugate base of that hydrogen fluoride weak acid. But you'll start to recognize the more that you practice these. The important thing, remember, is they partially dissociate, so there's always an equilibrium arrow when they react with water. Now that's important because, again, like weak acids, they only produce a very small fraction of the products compared to the reactants. Okay, so here's a summary of what we've learned about acids and bases. We've got the examples on the left: strong acids, hydrochloric, HNO3, sulfuric acid, hydrogen bromide. Strong acids fully dissociate. We expect them, if we have a 0.1 mole per litre solution, to have a constant pH of 1 to 3. Strong acids are good conductors of electricity because they fully dissociate to produce a high concentration of ions. Now, weak acids, we're looking at organic acids like ethanoic acids, ammonium ion, hydrogen fluoride. They partially dissociate. Their pHs are between about 3 and 5, right? Or they could be 2.7 or something like that. They have a pH that is lower than 7, but not super low like 1 and 2. They don't conduct electricity very well because they don't produce a lot of ions. However, if they are something like NH4+, where they are actually a weak acid, but they are also an ion, then of course they're going to conduct electricity well. Strong bases, sodium hydroxide, potassium hydroxide, lithium hydroxide, fully dissociate. They produce a pH of 13 to 14. They're good conductors of electricity because they produce a high concentration of ions. Weak bases, well, they partially dissociate. They're going to have pHs of somewhere between maybe 9 and 12, right? Or maybe 10 and 12, right? They are good or poor conductors. Now, they are good conductors if they started off as an ion, because the reactants are ions, they can conduct electricity. They are poor conductors if they started off as NH3 and they didn't produce many ions. You need to actually look at the situation and then resolve that. And that is a summary of acids and bases. Okay, so what are the type of questions we're going to have about this? Well, they're going to ask you to compare weak acids and strong acids, or weak bases and strong bases. So here's a question. I have a 1 mole per litre solution of weak ethanoic acid and strong hydrochloric acid. So I have two solutions. Now, often in the exam, they'll also say the pH of the ethanoic acid is 3.4 and the pH of the HCl is 1. So they might give you pHs just to help you out a wee bit here. I haven't, but let's take what I just said to help us out. So the first thing we're going to do is we're going to draw an equation for the reaction of, let's draw the weak acid. So the weak acid, we know, partially dissociates. We know it's going to donate its proton, so it's become 1 less positive, it's going to become negative. And if it's ethanoic acid, we know that it loses the proton next to the oxygen, right? So we produce this ethanoate ion and the hydronium ion. So I'm going to explain about this. So ethanoic acid, CH3COO-, is a weak acid, so it partially dissociates in water. Only a very small concentration of COO-, CH3OO-, and H3O+ ions are produced, so it will have a higher pH, 3 to 6, and it will be a weak conductor of electricity. Now, I might have expanded on why it's a weak conductor, because I could have said, hey, because the concentration of ions is low, and I could have expanded on the H3O+ ions and said, hey, it's because it produces H3O+ ions, its pH is going to be smaller than 7, but because there's only a smaller concentration, its pH is between 3 and 4. Now, if I went and I'm comparing it, remember, against a strong acid, here's a strong acid. I've drawn the equation HCl plus H2O. I draw a single arrow going to H2O plus Cl minus. It fully dissociates in water. Now it produces 1 mole per litre of H2O plus and 1 mole per litre of Cl minus. It will have a pH of 1, right? It has a pH of 1 because if I put that into a calculator, I would get, if I put negative log 1 time negative log 1, actually I think I'd get a pH of 0. Anyway, it's got a really low pH. Because the high concentration of ions, well, there's actually 2 moles per litre because there's the H2O plus the Cl minus, there's a lot of ions. The solution will be good conductor of electricity. Ions can transfer charge in solution. So I've actually linked it conducts because there's a high concentration, so that doesn't matter. I didn't put it in the first sentence. And I've said that it can transfer charge because that's what ions can do. Okay, well, that's reasonably thorough, so let's go and look at the next example. Okay, so if we produce a salt from a strong acid, it's always going to be neutral. Now the salt will have the chloride, the nitrate, the sulfate ions attached to it, and when placed in the water, the salt just separates into positive and negative ions because it is a salt. So examples of salts would be sodium chloride, right? If I put sodium chloride, it's an ionic solid, I put it in water, it separates into sodium ions and chloride ions. Now, because we know that a chloride ion is the conjugate base of a strong acid, we know it's neutral. Any negative ion produced from a strong acid is always neutral. So I can recognize this as neutral because it has a chloride there. And same with sulfate. I can recognize that sulfate comes from sulfuric acid, so this is going to be neutral. This is a salt. When we have to, now, when you are doing your exam, you'll recognize that they are referring to something being a salt or it being neutral because the pH will be 7. And when we put these ionic solids, we need to think about them in this way, and when we put them in a solution, they just dissociate and they break into ions. They will have a pH of 7. Also, they're going to be really good conductors of electricity because there's a high concentration of ions. Okay, weak acid salts. So this is a substance that is an ionic solid, so it's a solid that contains a positive ion that is a weak acid. So when placed in water, the substance will go through 2 equations. First, it's going to dissociate. So notice that we have a positive ion, which is the ammonium chloride. So this is a weak acid salt, right? So in that it's going to produce a weak acid when it dissociates. So we put this salt into solution and it becomes chloride ions and ammonium ions. Now we know that the chloride ions are neutral, right? But the ammonium ions we should recognize as being an acid, a weak acid, because this is the conjugate base, or this is a proton added to ammonia, and ammonia is a weak base. So we need to recognize ammonium ions as weak acids. That's one of the ones we need to remember. And now if it's a weak acid, it's going to go further and react. Now remember, the chloride ion is just a spectator here, and it's also neutral. So the positive ion is a weak acid, so it's going to partially dissociate with water. So in the first instance, we're producing a high concentration of these ions. Then it is a high concentration, fully dissociates. So the first instance, it fully dissociates to produce the ions. And then the ions here, the weak acid, is going to partially dissociate and produce a small concentration of H2O plus and ammonia. Now, the salts, weak acid salts, are things like ammonium chloride or methanamine chloride. So they're going to be, well, they also could be, it could be weak acid salts. What else? No, that's about right. They're usually going to go with ammonium chloride. Now, you're usually going to have to explain, does this conduct electricity well? You're going to say yes, because in the first instance, it fully dissociates, produces a high concentration of ions. Those ions don't disappear because only a small amount of them, of the ammonia ones, the chloride ones do nothing. Only a small amount of the ammonium ones actually react with the water. All right. The pH is going to be smaller than 7 because we produce some hydronium ions, but it's going to be about maybe between about 4 or 3 to 5 because it only produces a lower concentration of H2O+. Weak base salts. Okay, so we can have weak base salts as well, and that's when we have a negative ion that is a weak base. So an example here is sodium ethanoate, right? So this is, in the first instance, it's just like the salt of a weak acid salt. So it dissociates, so it splits into sodium ions, which are spectator neutral ions, and ethanoate ions. Now the ethanoate ions, you realize, is the conjugate base of the weak acid, ethanoic acid. So it itself is a weak base, and we need to remember that that's acting as that is a weak base. So the negative ion is a weak base. It's going to go on and partially dissociate it with water. So when you see that these substances, when they are salts, ionic substances, ionic solids, right? They're going to have metals and non-metals. You're going to recognize them because you'll recognize what ethanoic acid looks like or ammonia looks like. When you see these salts, you're going to, it splits apart into the positive and negative ions. If it's a weak acid, it's the negative ion, it's going to be a weak base. If it's a weak weak acid, the positive ion is going to be a weak acid. If it's a weak base, the negative ion is going to be a weak base. And the next step it's going to do is that negative ion is going to partially dissociate with water. So the ones that you might recognize as weak base salts are sodium ethanoate, sodium carbonate, and sodium fluoride. There might be other ones that they might tell you about, but those are usually the go-tos. So again, because this is a salt, the first instance, it produces a high concentration of ions that are still around, so therefore it conducts electricity well. pH between about 9 and 11, because remember, it only produces a small concentration of OH minus, but there are more OH minuses than there are H2O pluses, so it is a higher than 7 pH. Okay, so here's an example of the type of question they might give you. Discuss the pH and conductivity of the salt sodium carbonate. Include all relevant equations in your discussion. Okay, so this here is a carbonate, so we know that it's going to produce sodium ions that are neutral and carbonate ion that it's negative, so it's going to be a weak base, right? So first thing, the salt fully dissociates in water. Let's show that. Sodium carbonate, put an arrow with water over it, turns into 2 sodium ions and carbonate ions. Now remember, the sodium ions are going to be spectators. It's the negative ion, because it's a weak base, that we're going to go on and react with, or partially dissociate with, the water. So that partially dissociates with water, it accepts a proton, becomes hydrogen carbonate and hydroxide ion. So those are the two equations. That's great, but now we need to unpack them, we need to explain them. So as a sodium carbonate fully dissociates water, it produces a high concentration of sodium and carbonate ions, so it will conduct electricity well. That's the first thing we need to talk about. The second thing, as the carbonate ion partially dissociates with water, okay, we could say as the carbonate ion is a weak base and partially dissociated with water, the concentration of OH is low, but still higher than H2O plus concentration, so the pH is about 10 to 7. It's important to put that wee caveat there that we know that it's still higher than the H2O plus, but it's low compared to what a strong base is. So that would be a good explanation of if you were explaining the pH and the conductivity of a weak base salt. Okay, so you also might be asked to compare solutions. So here's an example. 3 solutions, 0.1 mole per litre, X, Y, and Z have lost their labels. The labels are known to be hydrochloric acid, potassium nitrate, and ethanoic acid. Okay, the pH of each solution is recorded below, so they've given us the pHs. We need to associate which is which. Let's go for the easy one. HCl, strong acid, it's going to be 1. So HCl is Y. Cool. The second one is, we can see ethanoic acid there. We know ethanoic acid. We've remembered our weak acids. This is a weak acid, so that's going to be the 3.4. That means the other thing that's at 7 must be a neutral salt. And it looks neutral because, look, it's got potassium. We know potassium and sodium are neutral ions. And we know that nitrate is an ion produced from a strong acid, negative ion, and we know that those are neutral. So we now have to then unpack this and explain it. So solution Y must be hydrochloric acid, as it is a strong acid and fully dissociates in water, producing 0.1 moles per litre concentration H2O plus, right? Or we could just say a high concentration. Solution Z must be potassium hydroxide, as it contains neutral potassium ions and nitrate ions, so I'll have pH of 7. Solution X is ethanoic acid. It is a weak acid, partially dissociated in water, produce a low concentration H2O plus ions, therefore it will have a pH range in this range, but not as small as a strong acid. Right? So I'm just in this question because they asked about the pH. I'm not talking about conductivity. I'm just putting each of my answers to talk about the pH. If I thought was necessary, I would support each one of these by equations. It might have been a good point. I should have done this anyway. I don't think they needed it here, but there's nothing wrong with putting more than they expect. Okay, last thing I want to talk about here is what is the word amphiprotic or amphoteric. So amphoteric means something that will react both as an acid or a base, or react with an acid and a base. Amphiprotic means it can either donate a proton or accept a proton. At this level, they're kind of both accepted. Okay, there is a slight distinction between the two, but we don't need to worry too much about that. So hydrogen carbonate is amphiprotic, as it can donate a proton when it reacts with a base and accept a proton when it reacts with an acid. So here it is, acting as a base. So hydrogen carbonate will accept a proton from the acid particle H2O plus, and it will become H2CO3 plus H2O. But if we put it reacting with the hydroxide ion, well, it's going to donate its proton, and it's going to turn into the carbonate ion in water. And that's amphiprotic, right? So if you have to explain or you need to show something being amphiprotic or amphoteric, you are just going to show it reacting with an acid or reacting with a base. And they've put those questions in the past and they might in the future. That's the end of this review video. Hopefully that's been helpful. Good luck with your exams. And let me know if you have any questions. Hey, put a like and put a comment if you found this helpful. Thank you.